In the previous video we saw that when we were dealing with a function of a complex variable z, we called zx plus iy and its image u plus iv. F of z is differentiable at a point z0 if and only if the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y, and the partial derivative of u with respect to y equals minus the partial derivative of v with respect to x. Let's look at the definition of the derivative of f at the point z0. So this has the same form as the derivative of a function of a real variable. We just change z0 by the amount delta z, we subtract off the value of the function at z0, and we divide by the change in z0, which is delta z. As we saw before, when we take the limit we can take it in any direction. So unlike the case of a function of a real variable where we only have two directions to consider, either taking the limit from the left or the right, we can approach z0 from any direction and along any path. It doesn't have to be a straight line path. So for example, we could approach z0 from this point. So this would be our z0 plus delta z, where the complex number delta z would be represented by this vector. It's actually pointing in this direction here. If we take this complex number and subtract z0, we get a complex number which we can think of as a vector with its tail at z0 and its head at z0 plus delta z. Now, our complex number z0 we can call x0 plus iy0, and if we add delta z onto z0, we get z0 plus delta, we get this nearby point z0 plus delta z. So it's like adding vectors. So it's like adding these two vectors actually. So this vector represents the complex number z0 and this vector here represents the complex number delta z. Now delta z involves a change in x, delta x, and a change in the imaginary part of the complex number z0, which we will call delta y. So we can write delta z as delta x plus I times delta y. Now taking the limit as delta z goes to 0 is equivalent to taking the limit of this quantity as both delta x and delta y go to 0. You can see if delta x goes to 0 and delta y go to 0, then obviously delta z goes to 0. And since the direction is unimportant, since we want this derivative to be the same regardless of which way we approach z0, we can take a simple case. That is the case where we approach z0 along a line that's parallel to the real axis. So if this point is z0, then the nearby point is z0 plus delta z. So this is the general picture up here. Well, we can z0 plus delta z can be anywhere near, but let's suppose it's on this line. So if you want to use vector notation, this vector here is delta z. Now the thing about any point on a line that's parallel to the real axis is that for delta z, delta y must be 0. The only thing that's changing as we go from this point towards z0 is x. We see no change in y. So the vertical distance between these points, delta y, is 0. So we can set delta y equal to 0 because this limit is path independent, and we can get our limit that way. So these terms don't appear. Now if we look at this here, we see that this is the definition of the derivative of f with respect to x. Actually it's the partial derivative of the function with respect to x. So here we have the function at z0, this term here, but over here all we've done is changed x by an amount delta x, so we haven't changed y, and we've divided everything by the change in x. That's just the definition of the partial derivative, but the partial derivative evaluated at z0 Now, f prime of z0 is a complex number because f of z0 plus delta z is a complex number. F of z0 is a complex number. The difference of two complex numbers is a complex number. Delta z is a complex number, so the whole thing is going to work out to be a complex number. Similarly for this limit here, we can write f of z as u plus iv, and when we take its partial derivative, we can just differentiate each of these terms with respect to x. So the real part, u, is in general a function of x and y. The imaginary part, v, is in general a function of x and y. So if we want to differentiate f with respect to x, we differentiate u with respect to x, the partial derivative of u with respect to x, and we have the partial derivative, or I times the partial derivative of v with respect to x. You can prove this if you go through the definition of the partial derivative of this function with respect to x. Just go through it from first principles. This I is just a constant factor. By the way, since we're working this out at z0, we could put the derivative of u with respect to x evaluated at z0, and the same here, where z0 is x0 comma y0. Now, since the limit doesn't depend on the path, we can take a different path. Now this time we'll take a vertical path. So here is a nearby point, z0 plus delta z. And we can see here that delta z does not involve delta x. The horizontal distance between these 2 points is 0. So we see the delta x terms disappearing. So we just have I delta y in the denominator. You can see that we haven't changed x0 by any amount, but we have changed y0 by the amount delta y. So I'll just factorize I out of this. Now we can also factorize 1 out over I out of this limit. It's just a constant. If we multiply above and below by I here, we'll have I over I squared. Well, that's I over minus 1, or minus I. So this thing is just minus I. So you see, we've changed y0 by the amount delta y, we've subtracted off the function at z0, and we've divided by that change delta y. Well, this is just a definition of the partial derivative of f with respect to y. And in this case it's evaluated at z0, but we can drop that z0 later. So again, as before, f is a complex number. We're differentiating it with respect to y, so we have to differentiate the real and imaginary parts of f with respect to y. So we have to get the derivative of u with respect to y, and then we have I times the derivative of v with respect to y. And both of these partials are evaluated at z0. Finally, since, as I've said many times, we want this limit to be independent of the path, so we want this result here to equal this result here. So I'm going to drop the z0. Okay, so the function is meant to be differentiable at z0, but let's suppose it's differentiable at some general point z. So, you know, this will be evaluated at z. So z is some general point. We assume that each of these derivatives is can be evaluated at. Okay, so that's this one here. And what's this one here? Well, what's the real part of this complex number? Well, it's minus I by I. That's minus I squared, which is plus 1. So the real part of it is plus 1 dv dy. And the imaginary part is minus I du dy. So these are two complex numbers that involve taking the partial derivative of u and v with respect to x and y, and then evaluating at a point that the function is differentiable at. So I won't show that notation. We know u and v are functions of x and y. So anyway, we get these two complex numbers, and the only way two complex numbers can be equal is if the real parts are equal and if the imaginary parts are equal. So if dv dx equals minus, including the minus sign of course, du dy. So these are the Cauchy Riemann equations. Now the way that I remember them is u comes before v in the alphabet. Okay, so our function is u plus iv. Okay, I had that written down, it's gone, but we differentiate the real part of the function with respect to x. X comes before y in the alphabet, and we differentiate the imaginary part with respect to y. So this one is fairly easy to remember, but this one here is more tricky. We just have to swap these and stick a minus sign in front of one of them. Of course, it doesn't matter which one we stick the minus sign in. So we just swap the x and y here in the denominators and change the sign of one of these derivatives. So we've proven that if f is differentiable at the point z0, then these two equations are true at the point z0. Now the converse of this is also true. That's what's meant by an if and only if statement, of course. So if these equations hold at a point where u and v are the real and imaginary parts of the function f respectively, then we can conclude that the function f is differentiable at the point z0. Now I won't prove that, at least not here. Let's take this example, f of z equals z squared. Now this function is differentiable at every complex number z. So we should find that the Cauchy Riemann equations hold at every point xy or z. So since z is x plus iy, we square it out to get this here. So the real part we call u, so u is a function of x and y. The imaginary part v is 2xy. Let's check this first equation. We need to take the partial derivative of u with respect to x, so we treat y as a constant. When we differentiate x squared, we get 2x. When we differentiate y squared, we get 0. We need to take the partial derivative of v with respect to y, so we treat x in this expression here as a constant. We differentiate with respect to y, so we just get the constant in front of y, which is 2x. So there we go, du dx equals 2x, dv dy also equals 2x, so the first equation holds. Let's look at du dy. So we want to differentiate this expression with respect to y, so we treat x as a constant. So when we differentiate x squared, we get 0. When we differentiate minus y squared, we get minus 2y. So that's what we have here. We need to get dv dx, so we need to differentiate this with respect to x. We treat y as a constant, so we just have the constant 2y multiplied by x. So when we differentiate with respect to x, we get 2y. Now you see that du dy equals minus dv dx. We just minus this here, we get du dy. And you see that it doesn't matter what z0 is, or the point x comma y is, these relations hold. We can also consider the converse of our theorem, which I didn't prove. We can see that since the Cauchy Riemann equations hold for all points x, y, we conclude that f of z is analytic everywhere, which means that f of z is differentiable at every point z in the plane.